Let's look at the energy balance for a pipe flow. So let's assume we have a fluid that is going through a pipe with the length of L and radius of R0, and this fluid coming with the mean temperature of I, TMI, with the mass of m dot, specific heat of Cp, and then going out with the mean temperature of O. Now, if I take a small element of this pipe, dx, so the fluid coming with the mean temperature of Tm, and then going out with the Tm plus dTm, the change of temperature, and there is a convection happens at the surface of this wall, Q convection. Now, if I write for this small element, dq, the change of the energy for the fluid that is flowing is going to be m dot cp dtm, and we know that for the flux that's going on around around this small surface area, dq convection is going to be q dot s. Let's say this is a surface flux times perimeter times dx. And this dq convection for a convective flux, q double prime s is going to be h ts minus tm. Now, if I make them equal to each other, like the change of the energy or heat that has been transferred. So if I write the balance of energy balance for this small element dx, what we are gonna get is m dot cp dtm. It's gonna be q double prime s p dx, which is equal to h ts minus tm p dx. Now, my goal here is to find out the variation of temperature, mean temperature Tm, as a function of x. So if I do small rearrangement here, dTm over dx would be q double prime sp divided by m dot cp, which is equal to the h ts minus tm divided by m dot cp. There should be a p here. Yes. So what this equation tells us is how Tm, this differential equation, shows how Tm varies with location x from the entrance of the pipe. Now, if I can evaluate these equations for two different boundary conditions that we discussed before, for constant flux and constant temperature, and from there I can get the temperature variation, mean temperature variation as a function of x. So the first one is Tm for constant flux we rewrite that dTm over dx is going to be q double prime s p divided by m dot cp. P is the perimeter, and for a uniform cross-sectional area is constant. M dot is the mass flux and it's always constant. And Cp, let's assume, is constant. Or it's not really temperature dependent. The variation is very small. Now, if I take the integral of this equation, what I'm going to get is Tm of x would be Q double prime S P over M dot CPX plus C1. Now for this pipe flow, I know at the entrance at X equal to 0, we have the mean temperature of TMI. So at X equal to 0, temperature is Tm and I. So if I do the replacement, then I can get the distribution or a function for the mean temperature variation with respect to X. It's going to be Q double prime SP divided by M dot Cp times X plus Tm and I. I can use the flux, convective flux, H Ts minus Tm to find out the surface temperature, the wall temperature. So from here, Ts, the tube temperature, tube surface temperature is going to be Q double prime S divided by H. We know that Q double prime S is constant, plus Tm, Tm of X. So through this energy balance equation, I can get the mean temperature of the fluid that is flowing and the surface temperature. So if I make a plot of that, let's say this is the tube that we have, x0, x equal to L, and we said there are going to be some fluid with the TMI average or mean temperature of I getting in. So this is X, and let's say this is temperature. X equal to L. So the fluid coming in at the temperature of Tm and I, and the temperature is increasing with the slope that we have, Q double prime S time P divided by M dot C, and going out. So this is the variation of temperature along the pipe. So this is the fluid that getting in. And remember that like for the constant flux, we had this temperature profile. That's how it was changing with respect to R. And then we were saying we are going to replace that one with the mean temperature. So this mean temperature Tm, this is how it's just changing along the X direction, along the pipe that we have here. And if I similarly plot the surface temperature, so this is going to be the surface temperature, Ts of X, and the difference between two would be this Q double prime S divided by H. So the mean temperature for constant flux varies linearly along the X with the slope of, so the slope here is going to be Q double prime S P divided by M dot Cp. And the surface temperature also along varies linearly with respect to the X, and the distance between them is going to be constant, and that constant is going to be Q double prime S divided by H. Next, I will do the same analysis, but for a constant wall temperature.